Examples of finite sets, Introduction. So let's move on to looking at some examples of finite sets. As you recall from our previous discussion, we defined a finite set as a collection of items, or elements, where the number of items is countable. That is, you should be able to count the number of elements in the set and arrive at a whole number. Now, what does countable really mean? It means that, theoretically, we can list out all the elements of the set, one by one, and eventually we'll reach the end of the list. There won't be any elements left to add. It's important to emphasize the eventually reach the end part. That's what makes it finite. In this section, we're going to look at several examples to really make sure you understand this idea of a finite set. We'll be looking at examples you encounter in everyday life, like things in your classroom, and also some examples that come from mathematics itself, like prime numbers. By working through these examples, you'll be able to confidently identify whether a given set is finite or not. We'll be breaking down each example step by step, so don't worry if it seems a little abstract right now. We'll build up your understanding as we go. Real-life examples, students in a classroom. So let's move on to our first example of a finite set. As we discussed in the introduction, a finite set is one where we can count all the elements. This example focuses on students in a classroom. Imagine a classroom with 25 students present. We can represent all these students as a set, and we'll call this set S. So, S will contain all the individual students in that classroom. Now, to actually write this set, we would list out the names of each student. It would look something like this: Alice, Bob, Charlie, and so on, all the way up to Zoe. We use 3 dots and ellipsis to indicate that the list continues, but we don't need to write out every single name. The set S, therefore, contains 25 elements, each element being the name of a student. The key thing here, and this is what makes it a finite set, is that we can list all the students. There's a definite stopping point. We know there are exactly 25 students in the class. If we tried to keep adding more, we'd be imagining students who aren't actually there. Now, let's break down how we confirmed this is a finite set, step by step. First, we identify the elements. In this case, the elements are simply the individual students themselves. Each student is a member of the set. Next, we count the elements. The problem tells us there are 25 students, so we know the set contains 25 elements. Finally, we determine finiteness. Because we were able to count the elements and arrive at a final number, 25, we can confidently say that this set is indeed finite. This is a simple example, but it illustrates the core idea. If you can list all the items in a set and eventually stop, it's a finite set. We'll see more examples, including some mathematical ones, in the following slides, building on this same principle. Real-life examples, days of the week. Let's move on to our next example of a finite set. As we discussed in the introduction, remembering that a finite set is one where we can list all the elements and eventually stop. Now, let's consider something very familiar, the days of the week. This is example 2. We can definitively say that the set of days in a week is a finite set. To represent this mathematically, we use set notation. We're defining a set and we're calling it D. That's D as in days. It's represented as a capital letter, and the elements inside the curly braces define what's in the set. So, we have D equals an opening curly brace, then we list out each day. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and then a closing curly brace. This set D contains 7 elements. That's pretty straightforward, right? We can easily list all the days of the week, and importantly, there are no more. Once you say Sunday, you've listed them all. There isn't another day of the week to add. Now, let's break this down step by step, just to make sure we've really understood it. First, we identify the elements. In this case, the elements are simply the names of the days, Monday, Tuesday, and so on. Second, we count the elements. As we already established, there are 7 days in a week, so there are 7 elements in our set D. Finally, we determine finiteness. Because we were able to list all the elements, all 7 days, and we know there are no more, we can confidently say that this set is finite. This example, like the one with the students in the classroom, reinforces the idea that if you can list all the items and reach a definite end, you're dealing with a finite set. We'll continue looking at more examples, including some mathematical ones, to really solidify this concept. In the next example, we'll look at the colors of a rainbow, which follows the same logic. Real-life examples, colors of a rainbow. Let's move on to our third example of a finite set. As we've been doing, we're looking at things we can clearly count and list all the items in. This slide focuses on example 3, colors of a rainbow. Now, most of us are familiar with rainbows, and traditionally, we learn that a rainbow consists of 7 distinct colors. We can represent these colors as a set. We'll call the set C, and it will contain the following elements: red, orange, yellow, green, blue, indigo, and violet. So we write the set as C equals an opening curly bracket, then red, orange, yellow, green, blue, indigo, violet, and then a closing curly bracket. Remember, the order within a set doesn't matter, but we've listed them here in the typical rainbow order. Now let's determine the number of elements in this set. If we simply count the colors listed, we find that the set C has 7 elements. And this is key to understanding why this is a finite set. We can list all the colors, red, orange, yellow, green, blue, indigo, and violet, and there are no more colors in the traditional rainbow. We've reached a definite end. Let's break this down step by step, just like we did with the previous examples. First, we identify the elements. In this case, the elements are simply the names of the colors that make up the rainbow. Second, we count the elements. As we already established, there are 7 colors, so there are 7 elements in the set. Finally, we determine finiteness. Because we were able to list all the elements and arrive at a final number, 7, we can confidently say that this set is finite. This example, like the others, reinforces the idea that a finite set is one where you can, in principle, list every single element and eventually stop. We'll continue to build on this understanding with more examples, including some mathematical ones, as we move forward. Remember, being able to identify the elements and count them is the core of determining if a set is finite. Mathematical examples, prime numbers less than 20. Let's move on to our next example of a finite set. As we've been doing, we'll start with a real-world-ish concept, but this one is more mathematical in nature. Now, remember from our introduction to finite sets, the key is whether we can list all the elements. First, let's quickly remind ourselves what prime numbers are. The slide states that prime numbers are numbers greater than 1 that are only divisible by 1 and themselves. So, a prime number has only 2 factors, 1 and itself. Think of 7, the only numbers that divide into 7 evenly are 1 and 7. Now, let's identify the prime numbers less than 20. They are 2, 3, 5, 7, 11, 13, 17, and 19. Notice how we can systematically find them by checking divisibility. We can represent this set using set notation. The slide shows this as P equals the set containing 2, 3, 5, 7, 11, 13, 17, and 19, where the elements are enclosed within curly braces. If we count these numbers, we find that the set P contains 8 elements. And this is crucial. We can list all the prime numbers less than 20, and we know we've listed them all. There aren't any others. This is what makes it a finite set. Let's break it down step by step, just to be absolutely clear. Step 1, identify the elements. As we said, the elements are the prime numbers less than 20. Step 2, list the elements. We've already done that. 2, 3, 5, 7, 11, 13, 17, and 19. Step 3, count the elements. We counted and found there are 8 of them. And finally, step 4, determine finiteness. Because we were able to list all the elements and arrive at a final number, 8, we can definitively say that this set is finite. This example builds on what we've already covered with the students in a classroom, days of the week, and colors of the rainbow. It shows that finite sets aren't limited to physical objects. they can also represent mathematical concepts. Keep this in mind as we move forward, because on the next slide, we'll look at common mistakes people make when identifying finite sets, and it's important to understand that just appearing limited isn't enough. You need to be able to definitively list all the elements. Mathematical examples, even numbers between 1 and 10. Let's move on to our fifth example. As we've been doing, we're continuing to build our understanding of finite sets with another concrete illustration. First, let's quickly recall what even numbers are. Even numbers are simply numbers that are divisible by 2. That means when you divide them by 2, you get a whole number with no remainder. So what are the even numbers between 1 and 10, including 1 and 10? Well, they are 2, 4, 6, 8, and 10. We can represent this set using set notation. We're calling our set E, and it's defined as E equals the set containing 2, 4, 6, 8, and 10. If we count the elements within that set, we find that the set E contains 5 elements. And just like with the previous examples, the students in a classroom, the days of the week, the colors of the rainbow, and the prime numbers, we can list all the even numbers between 1 and 10, and we know we've reached the end. There aren't any more. Let's break this down step by step, just to reinforce the process. Step 1, identify the elements. The elements, in this case, are the even numbers between 1 and 10. Step 2, list the elements. As we already established, those are 2, 4, 6, 8, and 10. Step 3, count the elements. We have 5 elements in total. Step 4, determine finiteness. Because we were able to list all the elements and arrive at a definite final number, we can confidently say that this set is finite. This example, like the others, helps solidify the idea that a finite set is one where you can, in principle, list every single element without going on forever. We'll soon be looking at common mistakes to avoid, but for now, make sure you understand how we've identified these finite sets. Key takeaways. Let's recap what we've learned about finite sets with these key takeaways. First point, a finite set is a set with a countable number of elements. What does countable mean? It simply means you can assign a whole number to each element if you were to list them out. We've seen this in action with all our examples, the students in a classroom, the days of the week, the colors of the rainbow, and even the prime numbers less than 20. Next, and this is really the defining characteristic, you can always list all the elements of a finite set and eventually reach the end. Think about it. With the classroom example, you start listing names, and you know you'll eventually list the name of the last student. There's a definite stopping point. This is crucial. Now let's consider what these finite sets can represent. They aren't limited to just abstract mathematical ideas. As we've seen, finite sets can represent real-life objects, like the students in a classroom or the days of the week. But they can also represent mathematical concepts, such as the set of prime numbers less than 20 or the even numbers between 1 and 10. So, it's a very versatile concept. Finally, and this is important for understanding the size of a finite set, the number of elements in a finite set is always a non-negative integer. That means it's 0 or a positive whole number. You can have a finite set with no elements, that's called the empty set, or a set with 1, 2, 3, or any whole number of elements. You'll never have, say, 2.5 elements. These are the core ideas to remember about finite sets. In the next slide, we'll look at some common mistakes students make when identifying these sets, so we can make sure you've really got a solid understanding before we move on. Common mistakes. Let's move on to the final slide, which highlights some common pitfalls when identifying finite sets. This is really important, so pay close attention. A common mistake is to assume that a set is finite simply because it appears to be limited. What this means is, just because something seems like it has boundaries, doesn't automatically make it a finite set. We need to be careful not to jump to conclusions. It's crucial to ensure that you can definitely list all the elements. Remember, the definition of a finite set is that you can, in principle, list every single element and eventually stop. So, before declaring a set finite, you need to be absolutely certain you can create that complete list. For example, if you were asked to list all the fractions between 0 and 1, you would find that it's impossible to list them all, making it an infinite set. Let's think about that. Between 0 and 1, you could have 1/2, 1/4, 3/4, 1/3, 2/3, and so on. But you could also have fractions like 1/5, 7/10, 1/100, and you can keep going forever, creating infinitely many fractions. Because you can always find another fraction, this set is not finite. Always consider whether the set has a definitive end or if you can always find another element. This is the key takeaway. Ask yourself, if I start listing the elements, will I eventually reach a point where there are no more? If the answer is no, then the set is infinite, not finite. So, keep these points in mind as you practice identifying finite sets. It's not always as straightforward as it seems, but with careful consideration, you'll be able to confidently determine whether a set is finite or not. And that brings us to the end of this section on finite sets.